Now this illustration deals with the protection of equipment. And it's ground fault protection of equipment to be exact. And notice in the note 1, to calculate the maximum allowed energy level, we always would start with a 2000 amp cycle as a constant figure that we would use or number. And notice the devices, they have to be 1,000 amps or greater. The system has to be 277 480. And if that's the type of system that we have, then we have to choose a method to provide ground fault protection that would give us adequate protection. Now notice the window type you see there is the very best. Current goes through the window, through the conductors, magnetizes the relay, current returns and demagnetizes. And when you set your relay from 0 to 1200 amps, then once your current exceeds the setting, it will open up the circuit and prevent 277 480 from just completely cutting the service all to pieces. Now, what we're talking about here, 277 480 volt systems have that restrike voltage capability of 250 volts to ground. And once a ground fault starts to strike to ground, it will continue striking. And it builds up a very high resistance that a large main will not detect and open. So usually, I remember when this came into the code in 1975, and the first job that I was on working that this occurred was a hospital. And we had just a drill motor go to ground on a 20 amp circuit, and it opened up the whole system. When we got reviewing it, what the reason was, that relay wasn't set. It wasn't set at all, so it just opened up. So we called the manufacturer, was talking to him about it, and we was new to this new rule in the 75 code under 230.95. And he said, well, just take 10% of your device and start there. So if it was 2,000 amp, we take 10% of that and set the relay at 200 amps. He said, now if it still fails to function properly, reliable, he said take 15% of 2,000. And if that still gives you a problem, a nuisance tripping, go up to 20% of 2,000. And if you still have a problem, we need to come out as the manufacturer and take a look at it. Now, back in those days, you had to talk and call and talk to an engineer. You couldn't go online and get a diagram and instructions like we can today using the internet. So that's what we did. But we were responsible to set it. Today, you know, it comes from the manufacturer, set. They'll set it. We just get a letter and present it to the authority having jurisdiction for their approval. So 230.95 lists these rules we're talking about for a service. 215.10 lists the rules for a feeder. And then if we looked at 210.13, I believe it is, that's the rules for a branch circuit. Now the next method we could use instead of the window is the donut type you see in the illustration. But it is not the state of art that we would use. Notice that it's connected to a grounded bar through a strap, it's a donut, that connects to the neutral bar that's isolated from the can, which the code permits, as we'll see. And the grounded conductor connects to that bar. But notice that all your, the leakage current due to a ground fault has to come back over your equipment grounding means. That's designed and installed by 250.118. of the NEC. So the window's the best type, but it costs naturally the more money. Now, note 1 to calculate the maximum allowed design level. Once again, use 2,000 amp cycles as a constant. Number 2, the FLA of a transformer times 6 produces the maximum ground fault, the MGFA. 6 is always used as a constant, is using this rule of thumb type method. And then note 3 says for the ground fault protection requirements, we could see pages 6-29 and 6-30 in this workbook, in this chapter. So this figure 6-51A is getting us started to determine where a ground fault might occur and how the settings would be set so that we localize the area where the fault occurs.